Okay, good. Yeah, apologies for being late. Addressing all your questions and then reparking my car apparently takes longer than an hour. So where were we? Here. Okay, we're going to just start manometry, right? And there's something referred to as a piezometer tube, which allows the measurement of a liquid. And so the liquid resides and then is also partially in this tube that is open to the atmosphere. And again, a very simple concept to measure the pressure in this liquid with specific weight gamma at point A. Okay? And one can read off this height, big H. And so we can start off with this, with our hydrostatic equation. H is depth measured down from a free surface that has at the pressure is at P atmosphere. So right at the free surface, we assume the pressure is P atmosphere. And then we go down in depth a distance H. And so we can apply this equation here. So P naught is P atmosphere. And then H is this distance, and then 0.1 would be the pressure at this at that location based on this. But P1, since it's at the same level as point A, then PA equal P1. Okay, so one can also express the pressure in terms of gauge pressure, which is then directly proportional to the height of this fluid column H, big H. And then the specific weight of the liquid. Okay, so it's a very simple device. Disadvantages, basically, the pressure has to be greater than P atmosphere, otherwise the fluid will get sucked in. PA relatively small, so that H is reasonable. Again, that since H. The pressure is proportional to H and this. So depending on the density of the fluid, H will be a certain height depending on the pressure. So the pressure has to be relatively small for H to be fit in the lab, for example. And then fluid A must be a liquid. So that's not, it's very limited. So then a U-tube manometer addresses some of these issues. So now we have a gas contained in this portion of the, we may have gas in a tank that we want to measure the pressure of. And so we can measure the pressure at point A, but since it's a gas, if this tank isn't humongous or tall, essentially it'll be uniform pressure. And then the blue is indicating the gauge fluid, which, for example, could be mercury or some liquid. And then there's a U-tube, and it's open to the atmosphere. Okay? So the pressure at this free surface is the atmospheric pressure. Now, in general, you need to be able to do a U-tube manometer problem, and it's a very straightforward process, and here are some basic rules that'll make things very simple. So we already know this basic expression here, and actually it might be more helpful to make this a capital H, so that we know it's a magnitude, some height of a column of fluid or a distance. Okay, and so let me do that. Maybe that'll clarify. So between any two locations, starting at a particular location, you go to point 2, okay? And if you go down, we know the pressure increases. If you go up, the pressure decreases, so plus or minus accordingly, okay? So that we already know. And we also know that the pressure at the same level through continuous fluid is the same, okay? And so to work out a manometer problem, you simply start at one location. Okay, so you can start here. Let's call this point 1. And then identify certain points or locations that are relevant. So this would be 0.2. And then we can say this is 0.3 at the interface of the gauge fluid and the gas. And then this is 0.4. And then we have point A. And then you just simply start at one end. So P1 is equal to P atmosphere. Okay? And now we go down to P2 from P1. And since we're going down, we know that the pressure increases. So this is going to be plus rho g, and H2 is the magnitude of this distance. Then from 2 to 3, this is the same level of in a continuous fluid. So that's this. So the pressure is the same. So P3 equal P2. And then we go from P3 to P4, we're going up through a gas. So we have P4 is equal to P3. So we're going up so that we expect the pressure to decrease. And now this rho g is of the gas. And then this one is of the, let's say this is mercury. For example, Hg. So this is Hg, right? And then that distance here is H1, magnitude. Okay, and then finally, PA, which we want, is equal to P4 because, again, it's the same level in a continuous fluid. Okay, then you kind of add them up. So the P1 cancels, the P2 cancels, the P3 cancels, the P4 cancels, and then you have PA is equal to P atmosphere plus rho g mercury H2 minus rho g gas H1. Okay? And then you could put the atmosphere, subtract it from both sides, and then you could get the gauge pressure. Now, this was the one in your notes. And so, okay, so we basically had this line. And as I mentioned, so, for example, if it was air and water, we've got the densities differing by 3 orders of magnitude. So in this particular problem, we could neglect, this is H1. H1 is this one, yeah. Okay, so if this, then we could neglect this. If you want to be precise about it, include it, and then you can see the difference in magnitudes. And then, but the way these things work, the gas specific weight will be so much less than especially if we're talking about mercury, the specific weight of the gauge fluid. So then we have the PA minus P atmosphere on the one side, which is PA gauge pressure of the gas, equal to, the height of the mercury column, H2, okay? So you would say, so many millimeters of mercury. Mercury then would allow you to evaluate the specific weight, okay? So that's pretty straightforward, and you should be able to do maybe something like this I'll assign to you in the homework with several different gauge fluids. And that way you can sort of control the resolution or, depending on the pressure that you want to evaluate, you want to be able to have enough precision. One way to do that actually is to have an inclined tube manometer. Okay, so rather than this tube here is inclined, and so now if you do the same thing, so identifying locations. So here I guess I sort of numbered in reverse. So this is point A, point 1, point 2, point 3, open to the atmosphere. So I started here again, P3 equal P atmosphere. Now going down from 3 to 2, of course, it's the vertical height that the pressure change is proportional to. Okay, so this vertical height is going to be this distance, which is the reading. Okay, so the glass tube is going to have, tick marks, and we can then do the read off this length. Okay, and then there's an angle. So sine theta would give you the vertical height, which will give you the pressure change between here and here. Okay, so we have then P2 is equal to P3. Okay, and then we're going down. Okay, so plus gamma B L sine theta. So B must be the gauge fluid. Then P1 equal P2, same level through a continuous fluid. And then okay, then I already did this. So this is through gas. So I'm just saying this is this. So, so P1 equal P2, and then PA equal P1 minus, looks like there's an error in my notes. This should be negative, right? Because we're going up. Wait, PA, no, we're going down. PA, no, we're going up, yeah. So P1 minus this. Okay, so then this is negative. Does that look right? And again, if this is a gas, then we could neglect this term, and then solving for PA minus P atmosphere, okay, or the gauge pressure, then you get gamma B, specific weight of the gauge fluid, L sine theta. Or if you solve for L, so L would be the reading off the glass tube. Okay, so that's this distance. Solve for L and you get the gauge pressure over gamma B times 1 over sine theta. And so now this is like a magnification factor, because for small angles, like as theta goes to 0, sine theta goes to 0. So this is like a magnification factor. So if you have a small pressure variation that you want to measure, and then you can use an inclined manometer so that you can have sufficient resolution or have a larger differential reading corresponding to that small pressure variation that you want to measure. Okay? Okay, but basically very straightforward, I think. So you should know how to do a manometer problem, so I'll give you 1 or 2 in homework 2. Okay, so now the last main topic main topic, and probably it is sort of the main topic in Chapter 2, is to evaluate hydrostatic forces on submerged surfaces. So here's a surface here, okay, that is submerged, and so we've got, say, water. This could be a surface of, say, a dam or some structure in the water, or you could have some object underwater, and you want to basically know what the force associated with the fluid pressure is on a particular surface or object, okay? And we know if we assume that the fluid has constant density, then there would be a linear variation of pressure. So here, if we choose as our coordinate depth, starting from 0 at the free surface between the water and the air, okay, and then at h equals 0 is the atmospheric pressure, maybe the sea level pressure, okay? Then from this value, P naught, as we go down in depth, the pressure increases, okay? So here I have this linear variation and a linear increase of the pressure in the water. And that pressure distribution is going to cause a net resultant force on some surface. Let's just look at this inclined surface, okay? And so we want to be able to evaluate that force, which will be a distributed force because the pressure varies along that surface, okay? And so we go back to the differential force due to the pressure, which equal minus PdA, okay? So that's our usual expression for the differential force due to the pressure. And again, for a surface like this, we know that the force due to the pressure is always going to act toward, oops. Oh, it's that sensitive thing going on. If I hold it down, it goes into that straight line mode. Sorry. So anyway, the differential force due to the pressure always still acting in the opposite direction as the outward normal, so always towards the surface. And then that the force is going to be increasing as you go down in depth. So in general then, the resultant force, the total resultant force, can be obtained by integrating the differential. Okay, so substituting this in here, we integrate over the area that we're interested in. So it could be this, or it could be a horizontal area or a vertical area, but in general it could be inclined. Okay, and so now we just have to integrate the pressure over the area. So the pressure, we have an expression for, wait, this is not here. So the pressure, P equal P naught plus rho GH. Again, H is a coordinate that we defined, measured positive downwards from the free surface. And then in this simple case of a vertical surface, okay, the area vector is always going to be pointing in the same direction to the left. Okay, so the force will always be pointing to the right. This differential area here is W, which I don't have written down. So it's going to be this distance, the vertical distance, which will be DH. And then the width could be some constant. If it's a rectangular surface, it could be a constant value W. Okay? And so the differential area equal WDH. And so for the vertical case, which I think what this was the simple case of a horizontal. Okay, so here we go. For the vertical case, so here's the surface. Here's showing either the linear pressure distribution, or you could think of it as the distributed force acting over the surface. Okay? And so we look at a differential force over a differential area. Okay, so the differential force is given by this. The P can be expressed in this way based on this coordinate system for this problem. Okay, and maybe we know the P naught. Okay, so then substituting in, and I said the differential area was this strip. So if I indicate that here, this would be like, so this height DH and this is W, so that's dA, scalar magnitude. Okay, so you just substitute that in here. Then you can see that you integrate with respect to H. So here's the H, and here's DH, and then here's the H. So then it's a very simple integration, right, for the vertical case. And what I had shown here is the even simpler case of a horizontal surface, which is at constant pressure, and that's why it ends up just being PA. So this here was the force due to the pressure on this horizontal, the bottom surface of maybe a tank. So you can see that it's very straightforward, right? Okay, so then if we just look at now the more general case. So an inclined surface, okay, that doesn't necessarily start right at the top, okay, so it could be submerged. Again, very straightforward, but you just have to do it one step at a time. The other thing, if you want to completely determine the resultant force, okay, so here we will have a distributed force, the pink, okay, And in general, you may want to then determine the resultant force. So this distributed force, okay, replaced with a resultant force, which to completely specify this, you need to know the direction. Okay, so it's always towards the surface. And for a planar and vertical surface, it's pretty straightforward, right? It's to the right. You also need to know, okay, the magnitude. So the magnitude for this case here, we have this. That was the magnitude. Third, you need to know the point of application of the resultant force. Okay? So that, in general, if this was, say, a gate, based on the distributed force, and let's say there's actually a gate and a hinge here. So let's say there's a hinge, and this is a gate. Okay? And if the force is sufficient, it would open up the gate, right? And a distributed force like this is going to cause a moment about the hinge. Okay, so then equivalent to that would be a resultant force acting at a certain location to cause the same moment. Okay? So those are the things that we need to determine for completely specifying the effect of a distributed force on a surface. So that's the goal here. Okay? And it's very straightforward. So we're going to now consider the more general case, as I mentioned, of an inclined surface that doesn't necessarily start right at the free surface. But in general, we can, so in general, for a liquid, we could assume constant density. But as I mentioned last hour, be prepared to do something like this where the density varies. Again, if you just follow the steps, it's very straightforward. Okay? But see, you have to set the problem up to indicate the assumptions. So for this derivation, we will make it simple, and we're going to assume density is constant. There's a free surface, liquid, and above is air. At the free surface, the pressure is known, P naught. Okay? And for this constant density case, we could go back to the general hydrostatic equation, integrate, and we would get this expression, right? So at H equals 0, P equal P naught, linear increase. So there's our pressure profile. Now, let's consider this inclined surface. This pressure distribution will result in a distributed force, which I so nicely drew with the straight line option. And again, the force is always, whether it's a differential force or the resultant force, always acting towards the surface. Okay? All right, and then we're going to evaluate the force on the upper surface. Now, I could give you a problem where you evaluate on the lower surface, but in general, the same concept. Okay? And we know that the resultant force, which is a vector in general, is given by this expression. And then in this slide, I just emphasize that to completely specify or determine this, we need to know the direction. For a planar surface, this is by inspection. Okay? So it's towards the surface and aligned with the normal to the surface. The magnitude, okay, we can get by integrating this, doing the integral. And then just worry about the magnitude. And then the point of application is all about equating the moment caused by the distributed force must be the same as the moment caused by the resultant force. And I'll show you that. Okay? All right. So here's the problem. And so we always need a coordinate system. So it's convenient to define one of the coordinate axes along the surface. Okay? So we define y along the direction along the surface, origin at the free surface. Okay? We can then consider z as being perpendicular to this surface, and then x into the page. Okay, so there's our xyz Cartesian coordinates. And then we can still use the depth coordinate to describe the pressure variation. So again, H, origin of H is at the free surface, where we know the pressure P naught. Okay? Now, we have our differential force. So here's the differential area. Okay? dA, the vector pointing outwards. And we're interested in this top surface here to determine the force on. In general, a differential area could be dy length and also dx into the page if this shape here is some irregular shape. So that shape could be if we look at the projection, I mean, the shape could be maybe even like a triangle or something, so that it makes sense to do, a dx dy, or just even some shape like this. But FYI, we're going to consider in 101A here the simplest case of planar, not curved, and rectangular. Okay? And the main thing is, because I don't want you to worry about the curved surface and things getting very complicated. I should have just done undo. Because really what I want you to do is understand this very basic idea, which is actually quite simple, straightforward, okay? All right, so now, as we did with a vertical or horizontal surface, so you have the pressure distribution given by this in terms of the H coordinate, okay? And then here in the integral, so now let's just take the magnitude. So we don't worry about the negative, because that was to indicate direction. We already know the direction. It's towards the surface. So the magnitude is just going to be this. And P, now, the dA, okay, in this case, is going to be with dy, not dH, as in the vertical surface. Okay? So ultimately, this dA, if it's a rectangular surface, so of constant width into the page, is again going to be like a W dy. But now we're going to have dy here, and the pressure expressed in terms of H originally. So we need to express H in terms of Y, since this is going to end up being a W dy. So just looking from the schematic at any dA, okay, we can get H, the depth of this differential area, in terms of the Y coordinate, which is measured here. And just from the geometry, it's going to be y sine theta. So if you know this inclination angle, you can easily express H in terms of the y coordinate along the surface. Okay, so then you replace that, and so you have this for the P, dA, and then substitute in dA equal W dy. And now it's just going to be a very simple integration, right? And the limits of y, okay? So the surface starts here. So, oh, here, I have a schematic. The surface starts here. So if you know this distance, okay, so you start the integration from y equal s. And if you know the length of the plate, then the integration is y goes from s to s plus l. Okay, very straightforward. So then you can do the integration, and then you end up getting this. Okay? Note, if the upper edge of the plate is at the free surface, I'm saying, so if you have a situation where the surface starts here, okay, then S, this sort of displacement, is 0. So then you set S equals 0, and you get this. And if it was a vertical plate, then theta equal 90, sine theta equal 1, and then you get this, which is which is this, and this is just the same result as we got for the vertical surface. Okay, so this sort of generalizes it. Okay, so this should be very straightforward to do, and you need to know how to do all this, which is, I hope it was straightforward. Okay? And I'm saying this and emphasizing this because the textbook has equations that you may be tempted to just plug and chug. On an exam, I will examine you on your ability to just do exactly what we did. Okay? Starting from the general equation, and then this, and then the geometry. All right? All right. Now, so direction by inspection, we got the magnitude of the force. Now the point of application. So we replace that distributed force with the resultant force vector, and we need to know where it should be applied to have the same effect as the distributed force. So the point is that the moment has to be the same. The moments have to be the same. The moment caused by the distributed force and the moment caused by the resultant force has to be the same, so you essentially evaluate the moments and equate them. Okay? So a convenient thing to do here in our original layout is to take the moment about the x-axis, which is into the board. Okay? Then, moment of Fr, so that would be this distance, so this would be the moment arm, which is the point of application, the y-coordinate, where Fr should be applied to get the same effect as the distributed force. So this is what we're after. So y times yr times Fr, or the r cross f, right, is the moment caused by the resultant, and we want to equate it by the moment of the distributed force. So let's look at the differential force, okay, and then the moment caused by the differential force is going to be the moment arm, which is going to be y, the y-coordinate at that location, times df. And then we add up all the moments of the distributed force. So moment of distributed force is y, the moment arm, times the differential force df. Okay? And then you just set that equal to each other. So we already know what Fr is. Differential force we also know. So let's go back here. We already evaluated. So the differential force is just this guy, PdA. And so PdA can be expressed in terms of y dy, right? So this is the PdA, which will eventually give you the WD. The dA gives you Wdy. Okay, so the PdA, this is the dA, so you got PdA, and then here's y, okay? And then substitute in for p, again, the same expression, okay? And so then you get this, and then we take the integral again from s to s plus L, and these are very simple integrals, right? So you just do the integration, and then you want to solve for yr. So that is the point of application of the resultant force. And you already had Fr. Okay, that was the magnitude. And so you just divide this by Fr. Okay, and then you're going to get something like this. Okay? It's just very straightforward. So just a note, going back to that simple case, so if we took this expression and evaluated it for that vertical surface that we initially considered, let's see, then sine theta would be 1, and sine theta would be 1, and then the s is 0, this displacement. Okay? Now, furthermore, let's say we had this, maybe it was a vertical gate, and on the other side was the atmosphere. Okay, maybe it's a dam. Okay? So we have water on this side with the distributed pressure distribution, and on the other side, it's open to the atmosphere. So there is a constant pressure, the atmospheric pressure acting on this side of the gate or surface or object. Okay? Then you see P naught starts, the pressure distribution starts from here, and there's that constant part of the pressure on the submerged side. So P naught would act on the same on both sides, so you could sort of cancel out those terms, and then you get this. Okay, and if you then work this out, the moment arm for this particular example, the moment arm would be 2/3 L, which kind of should ring a bell if you did statics and you considered a beam. You know, you've kind of already done this sort of thing before, right? And then you have this 2/3 L result. Okay, I'm just have this summary slide for what we just discussed. Very straightforward. Direction, always perpendicular towards the surface, so you can do by inspection. The magnitude, so then you don't worry, this is just scalar quantities, right? And again, a little note to remind you, if density is constant, you can just substitute in. This is the result that we got when we integrate for constant density. If it's not, maybe someday I'll give you a problem where the density is not constant, then you have to go back to the dpdh, the original differential equation. And then if I give you rho as a function of h, then you can integrate and get the appropriate p function and then do this, right? Okay, and then the point of application we just did. You sum moments or you equate moments. So I think it should be very straightforward, right? So I'll give you a couple problems for evaluating surface on a submerged surface in the homework too. Oops. Now, comments regarding the text approach. So the textbook, so if you consider, so let's see, what was this again? So let's consider the rectangular area. Oops. I'm just going to, you can read the details in the textbook, but I just want to make an important point. So, so by looking for the resultant force, the magnitude, you do this, and it comes down to integrating y dA, which happens to be the so-called first moment of area about the x-axis. And so if you recall from statics, this is equal to yc times a. Yc is the y-coordinate of the centroid of the area. Okay, so I have this little diagram here. And so if you can evaluate the centroid for any area, okay, then that information could be used to get the resultant force. And it can be actually expressed simply in terms of the pressure at the centroid of the area. And then for the point of application, you get this integral of the y squared dA, which is the second moment of area, or the area moment of inertia, denoted by this. And so for any area, you could look this up in your, in the textbook or statics, and then substitute it into this equation. I do not want you to do this method, because then it becomes sort of, you look up something and you plug it into the equation, and you could get the equation, the result, not understanding the basic physics, which was very straightforward, I think. Okay, so although this would allow you maybe to consider more complicated areas, maybe do things quicker, what I want to always emphasize is understanding of both the basic physics and the basic, equations and methodology. So we won't go into the more complex cases where there's a irregular or a different shape or curved surfaces. I just want to focus on the basic case and make sure everybody can do it just using the basic ideas. Okay? Does that make sense? Right? Now, it always is the case where somebody who's probably not here today and will forget to watch the recording will not have heard me say this, and what they'll do is on the exam, memorize these equations. I always see this. Memorize equations and try to evaluate things based on area moment of inertia, which they also memorized. And there's no, if they get the right answer, they'll get 1 point for the correct answer. But for showing the analysis, it won't be there necessarily, right? So I want you to learn just what I explained today, the basic ideas and the basic method from using the basic ideas. Okay? All right. Oh, it's perfect timing, right? I think I owe you guys a few minutes, and it's Friday, so I think this is a good place to end. And next week, there's a couple more secondary but important ideas. The idea of buoyancy, which will be covered fairly quickly. I think we'll maybe revisit the force on rigid body, or pressure distribution for a rigid body motion. But then we'll move on to fluid dynamics next time. So you can start looking over Chapter 3. And look out for homework 2. Probably we'll post late Saturday or early Sunday. Yes?